My talk today, I want to elaborate how we treat rocks as data objects. It's a great pleasure to be at Future of Mining event. I was saying earlier to Nathan that Australian Mining Monthly is one of my favorite publications. I read most of the articles there, and it's good to be an event that first time is managed by them. Title of my talk, as you know, is treating of the rocks as data objects. My name is Shahram Tafazoli. I'm the founder and CEO of Motion Metrics. I'm here together with Mark Muhija, the guy who is over there. He is a sales manager of our office that will open in Perth soon. We are with Motion Metrics International, where our tagline is extending machine senses. So, this is funny because I have zero mining background. So I'm here trying to explain why we need to sense rock fragmentation. So bear with me. What I've learned is that process of comminution, which is the grinding and crushing of ore, is the most energy intensive step in mining, which accounts for roughly 40% of the total energy used in mineral processing. Essentially take that and break those rocks, which has combination of ore and waste, to smaller pieces, making rocks smaller. And I was also surprised to learn that 4% of the world total electrical energy is used for this. That's a huge number. Ore grade in Australia, like the rest of the world, continue to decline, so we need more energy to move and treat additional waste material. And to optimize comminution, you obviously need to sense the rock sizes in different various stages of mining, which starts from the face of the mine right after the blast. Very simple. And it's no surprise that blasting is the least expensive way of reducing rock size, that first stage. So essentially, the better a job you do in the beginning, you are saving a lot more money, you are being environmentally conscious, and you are reducing that 4% energy used there. So, where do we need to do rock fragmentation? Easy, fast, and accurate rock sensing is needed both above the ground and below the ground. Above the ground on the bench face after blasting, inside the shovel bucket. I'll show you examples of how we do that. On the tray of haul truck bed, on the crusher, and on conveyor belt. Below the ground in block caving, inside the LHD bucket, on the rail cars, on crusher and conveyor belt. I may have missed some stuff here, but those guys who are in the mining, the more you sense it, the better you can optimize your process. So what's image-based rock fragmentation? You take an image, like this one. You delineate the rock boundaries. So essentially, you go and say big rock, small rock, and fines. The blue ones are fines. So you find the boundaries, and you need to apply what's called scaling to go from pixels to the actual size and draw what's called percentage passing curve. And typically, three numbers are of key importance, P80 being the top one, P50 and P100, which is the top size. These are the stuff that I have learned over the last few years in mining. So these are the steps of image-based fragmentation. So what about the physical size of rocks? We need scaling. So imagine you have this image which represents a rock, and it's formed with 20 pixels. You need to know what's the scale in terms of centimeter per pixel. So if this is 1.5 centimeter per each pixel, you multiply that, so your scale factor says that rock is 30 centimeters. That's essentially projection of a physical rock on the camera image. What are the conventional approaches to scaling? I'm going to talk about these three applications and how we are trying to do it differently. In the face of the mine, believe it or not, people for a long time, they have been using known objects like basketballs. Two-person job, throw the objects in, take a picture, take it back to the office, find where the basketball is, and use your scaling. It's not safe, and it has a lot of implications. If it's inside the bucket, obviously you can use the width of the bucket. So you are looking for known sizes. And on a conveyor belt, I actually researched that, there's two methods. One is you put the camera, let's say, 1 meter above the conveyor belt, and you assume it's always 1 meter. So if you have rocks on top of each other, you have inaccuracy. Or I know another company which they use a laser sensor. So it's a laser shining into, in the middle of the conveyor belt. So that's the conventional approach. This is the story as story unfolds. So in all of these approaches, we have safety and accuracy concerns. People walking and putting those basketballs on the mine face, or even worse, in an underground, in a block cave, is very unsafe. And that's where the last place you want humans be. Finding the sides of the bucket is not always accurate. You can see this is one of our own algorithms. You can see we didn't do such a good job. Not only that, the bucket can be tilted, and that means foreshortening improves accuracy. On the conveyor belt, you may have uneven surfaces. So if you are assuming a fixed distance, or you are assuming you are using one laser, it's not good enough. So I introduced the first approach we use, which is called, the device is called portometrics. So it's a handheld device. Previously, people were either using the known objects, open pit, or underground with the proper lighting to do fragmentation. That's how it was done before. When I saw this problem, I loved it. I saw inefficiency, and I'm going to address it. So the way we do it with portometrics, we do stereo imaging, 3D sensing of rocks. And so essentially, you can hold the device, take a picture, in a few seconds, you have fragmentation data. One-man job, very safe. And this picture shows an underground mine in British Columbia where we actually, with proper lighting, we did the same thing. So essentially, if you have 3D sensing of rocks, your problem goes away. So it does two things. One is 3D sensing. So every rock, think of it as a data object, and you're finding the dimension of every rock separately. So I'm not making any assumption about the surface being linear and so forth. And what else we added, which I'm quite excited about, after more than 15 years of looking into the segmentation problem, we have introduced AI-based segmentation. So essentially, we have thousands of images that are delineated by humans, and we use that to train our deep learning engine. And we have been quite impressed with the results. Initially, we are introducing it on the cloud. So Portometrics sends the images to the cloud. Our platform is called Metrics Manager Pro. In the cloud, we do AI-based segmentation. The good thing about AI-based segmentation, let's say in some particular scenario the result wasn't good, I just pass it to our guys and say, can humans go back and delineate this? And we retrain the coefficients. So the example I like to use is that the old code was getting bigger with the traditional image processing. In AI approach, your code is this much with some AI network, and all is getting bigger is your label data, which is easy. So I can release a new version of software next week with the new data learned. It's very easy. This is the underground application. That's the actual dense 3D points we got from stereo imaging. There's no LiDAR or other things there. Fortunately, rocks are a very good scene for stereo imaging, perfect for a stereo image. Similar to humans, where we have two eyes to see the world in 3D. So it's not a two-man job. It's a one person. You just hold the device and take pictures. So if I bring this picture to a human, I give the software tool and say, go delineate it, doing a good job can take anywhere 4 to 8 hours on that. With our AI-based approach, I'm happy to report that we are in the matter of around 1 second now. So just imagine same thing that can happen, but much, much, much faster. Actually, the result I'm showing here is a little old. Our newer approach is much better. You will see that a little bit later. But, so this is interesting. I have a video here. We have a power use of our portometrics, which happen to be in Peru. Our devices have GPS, even though we are not bringing into our cloud-based platform. But I asked our engineers to kind of show in the pit what they are doing with portometrics. So they use the Google Maps Map API to generate this 30-second video. Shane, can we run the video, please? So it's going to show the pictures that are taken with portometrics in different locations of the mine. So you see segmentation. Every rock is sensed in 3D. So this particular mine is a big mine in Peru, and it shows they cared about fragmentation on a daily basis. This is a power user of Portometrics. Every day on the cloud, at least 4 images are coming, as you can tell. So it's a big consultant in blasting industry. So I really like that when I saw that first. It's always a good pleasure when you see a real customer who has paid money is really getting a lot of value from the product. So remember, every rocks that you saw there was sensed in 3D. So this is our shovel-based platform. This is a picture of a Bucyrus shovel with full rocks. The embedded AI sent it to the cloud. And here's the result of cloud-based segmentation. I go back a little bit. So we use the width of the bucket on that one. So this is 2D imaging plus AI. We do have plan to add 3D imaging there. So again, sense everything in 3D because you can add accuracy. Let me show you another one. This is, I used one of the images yesterday. This is the rock images. This is pure AI working on that. It's amazing. In the worst case, I may have to go and correct 1 or 2 rocks. That's it. For 15 years, I've been after these results, and finally with AI, we managed to see that. So this is under the product we call Shovel Metrics. Does other things, but the focus of my talk here is on rock fragmentation. So we saw portable device. In the mining, shovel is right after blasting. And we are introducing 3D imaging with AI-based segmentation for conveyor belts. So we have devised this stereo imaging pair together with a GPU, powerful engine. It does everything. It does 3D sensing of the scene. It does the segmentation, and all it, at the end, sends the result to the cloud so you can start managing. Every rock is sensed in 3D. Remember, a conveyor belt can be very fast, 10 meters per second. So it has to be fast, short shutter time to get clear image. This is, we are happy to do it with 3D imaging and AI. This one, because this is a future of mining, I got to show something about future. I don't know if you know, this is asteroid 25143. It's called Itokawa. Japanese got to this asteroid in 2004 and took some images. So we have a consultant in space, and they are interested in rock sizes because the spaceship goes very close to the asteroid to take some samples, bring it back to Earth for analysis 4 years later when it gets to Earth. So I asked him to send us the images. This is the image. 1.2 seconds later without any training. I didn't do any training of asteroid images. This is based on the Earth images. So we sent the result back. For the space industry, they don't do delineation. All they do, they hire people to go individual rocks and say, what's the biggest distance? Biggest distance. So they will delineate 2 points because they want to see what is the rough sizes, whether the spaceship can get sample that or not. For example, if it got here, it may be too big. It can't get then suck it in, bring it back to Earth. But here is a more suitable. But going from pixels to dimension. So I feel actually good. This can be one of the first industries we take it from mining to space to show those guys that we do some technology here that can be useful for them. I was surprised they don't do this. In a space application, they do it manually. They hire people, low-cost job, give them lots of images, and all they do, they go click on the distances. So I got a wow when I showed those results. So we are looking forward to 2 asteroid missions are happening this year. One is by Japanese Space Agency, and one is by NASA. They are both, the Japanese are happening in 2 months, the NASA in 4 months. And I'm interested to get them to sign up for a subscription platform to do the fragmentation of their asteroid. I can talk more about that, but I thought this is future of mining. I got to throw that in. So we did a little bit of work on that. So at the very end, we have a booth. You can see all these demos and ask questions. I can show you a lot of shovel images. This was, again, talking about mine-to-mill fragmentation analysis. We are doing it on shovel, portable, and belt. And we have plans on crushers, on the trucks, on the lower shovel side. And thank you for listening to me. Thank you.